Hi there. It's time to do some practice problems for our Unit 5, Chapters 8 through 10. On your sheet, I have all of your equations at the top. Just to go over these one more time, AC stands for centripetal acceleration, the V is velocity, and the R is radius. FC is centripetal force, and then we have mv squared over r. So it's pretty much the same equation here, but it's just times m, because of course F equals ma. We've got a torque equation. Torque is equal to force times radius. And on the side over here, I've put the equation that we'll use rather often, and that is where we're balancing torques for a seesaw or something similar. You have some problems like this on the back of your Chapter 8 CP page where you have seesaws and two different sized kids on either side. So there you're balancing the torque. You're saying the torque on the left side is equal to the torque on the right side. And our equation on the bottom left is for conservation of angular momentum. Angular momentum is equal to the rotational inertia times the rotational velocity. Now, we have not ever used inertia in a calculation before. We only talked about it conceptually. That's because it's not something that we normally use for linear motion. We only use it for rotational in our calculations. You will not ever have to find the inertia. It will always be given to you. And the same is true for rotational velocity. I will not make you find rotational velocity using rotational kinematics. I will just give you these i's and these omegas, and you will plug in and figure out how the usually rotational velocity is changing. So there's, just like over here where we have one side and the other equal to each other, we're doing the same thing here. This is very similar to our linear momentum conservation where we had m1 v1 equals m2 v2, except now it's for rotational motion. And our last equation is Newton's universal law of gravitation. I told you that's the one that looks really scary. There's a lot going on here, multiple things multiplied together on the top, and then we have this d squared on the bottom. I am not going to have you plug in numbers and calculate a gravitational force just because this unit, we're treating it very quickly. I am going to have you do proportional changes like we practiced in class with the law of ones, and that we'll do on our last question on this worksheet. So if you're ready, we'll get started. Number 1, a 1,600 kilogram car rounds a turn at 10 meters per second. If the radius of the turn is 32 meters, what is the centripetal force required to keep the car tires on the road? Just like every problem we've worked in physics so far, the easiest way to get started is to label the numbers that we have to work with. We have a mass equal to 1,600 kilograms. We have a velocity of 10 meters per second. And we have a radius for our turn, which is 32 meters. We are looking for centripetal force. Once you have your givens labeled, you can look at your equation and find it. It's the one with the centripetal force in it, so it's pretty easy. Even though we have a lot of equations, it's usually pretty easy to pick out which one to use. So our equation is Fc equals mv squared over r. We're looking for Fc, so we can just plug in our m and our v. And the r. I get a lot of questions about whether we should say 1,600 times 10 and take the square of the whole thing on top, and the answer is no. We just want to square the 10. It's not mv in parentheses squared, it's just v squared. If we do that, we get and then we get our final answer, 160,000 divided by 32 would be 5,000 newtons. Question number 2. A penny sits on a turntable near the edge and another penny sits on near the center axis. Which penny requires more centripetal force to stay on? So this question is about a turntable, which we discussed in class. You guys don't have a lot of experience with, unless you DJ and you have a vinyl collection. Turntables or something that's kind of foreign to you. This turntable is rotating around in a circle, and they're asking us to compare the penny that sits on the edge of the turntable with a penny that sits right near the center of the turntable. Which one requires more centripetal force to stay on? So if you look at the equation Fc equals mv squared over r, you'll see that near the edge of our turntable, the V is going to be larger. And that's because the radius near the edge is larger. As we discussed in class, the bigger the R is, the farther you are away from the axis of rotation, the greater your tangential velocity is, that V. Since both the V and the R increase, the centripetal force is going to be bigger near the edge, mainly because of this square right here. Since if they both increased and then we didn't have the square, then it wouldn't make any change in the centripetal force. But since the V is squared, and that's going to make the top of our fraction bigger, the centripetal force is going to increase. In number 3, what velocity is required to give a 12-gram Hot Wheels car a centripetal acceleration of 0.65 meters per second squared if the curve in the track has a radius of 0.2 meters? Let's label what we've got. We have a mass. That mass is in grams, so we need to take a note of that. That's not a good unit to have. If we need to calculate with it, we're going to have to change it to kilograms. They give us a centripetal acceleration of 0.65. And the curve in the track has a radius of 0.2. So what question are we asking here? It was right at the beginning. What velocity is required? We are looking for V. We have an M, A, C, R, and V. And if you look up at the top for our equations, you'll see that this equation has the M, V, and R in it, but it's got centripetal force. Whereas our equation over here, centripetal acceleration, has what we need, AC, R, and we're looking for V. So that means that our mass, the 12 grams, is not needed. We don't need to use it. It's just an extra bit of information. Our equation that we'll choose to use is AC equals V squared over R. We have the centripetal acceleration, 0.65. We're looking for our velocity, and we have the radius. To get the V by itself, we're going to need to multiply both sides by 0.2. And when we do that, we get 0.13 is equal to V squared. So we need to take the square root of both sides, and that will give us an answer of 0.36 meters per second. Our next question is about a rusty water spout. The spout is turned on by spinning a wheel. If the wheel has a radius of 0.23 meters and a torque of 32 Newton meters, is required to turn the wheel, how much force will be needed? So the first number that they gave us is the radius. And the second number is the torque. and they're looking for force. Again, it's pretty easy to tell which equation that we're going to use from the top of our page. It's the only equation that has torque in it. And if you're trying to decide between this one with the F and the R, or this one with just one FR, you'll know it's not this one because there's nothing being balanced. If we're just talking about a single torque, a single force, and a single radius, then that's the equation that we're going to need. So our torque equals force times radius equation. We will plug in the numbers that we know. .32 equals F times 0.23. To get the F by itself, we'll divide both sides by 0.23. And we will get an answer of 139 newtons. Number 5, if you triple the length of your wrench, how will the amount of force required change to loosen a lug nut on a wheel? When they talk about the length of a wrench, what they're really talking about is the radius of the lever arm. And that is the radius that's in the torque equation. So they are tripling the R. If you triple the R, a good way to do this is to use the law of ones. If that's the equation that we're interested in. And we know this is going to be 3 times as big, and we want the torque to stay the same, then one thing you can do is you can either rearrange the equation or you can just plug things in. So if the torque stays the same, we put a 1 in there. We're trying to figure out what happens with force, so we're going to leave that as an F. And then our radius is going to triple. If you solve for F and we divide both sides by 3, then we find out that the force needs to be 1/3. If you don't want to solve this as a rule of ones question and plug ones and plug in your change, then you can just think to yourself, well, if the torque has to be a certain number, then if the force and the radius are in there and the radius is going to go up, then the force is going to go down. You'll apply less force. So you can think about this just by being intuitive and think, well, if I triple this R, it's going to make the force 1/3, because 1/3 times 3 is equal to 1. It would stay the same for the torque. All right, going to flip over to the back. Number 6 at the top, a meter stick is balanced at its center of gravity. A 35-gram mass is hung from the meter stick at the 20-centimeter mark on one side. What mass will be needed to balance the meter stick if it is hung at the far end? I'm going to draw a little picture to see if it helps you out with this one, because some people have a hard time visualizing this question. So this meter stick is hung directly in the middle. There's a 0 centimeter mark on that side, and there's a 100 centimeter mark on this side. It tells us that a 35-gram mass is hung from the meter stick at the 20 centimeter mark. And then they want to know what mass would be hung from the 100 centimeter mark and keep this thing balanced. So they're talking about balance. You see the word right there, balance. And that to me means torque, and hopefully it'll mean torque to you as well. We're going to use the equation F1R1 equals F2R2. Now, This is a little interesting because we have grams and we have centimeters, but I'll give you a little hint. You do not have to convert these into kilograms and meters because we have two sides. So if this is in grams on this side, this can be in grams over here. And if the R is in centimeters on the left, you can put the R in centimeters on the right. So that's a little time saver. It won't be hard to work these after all. Another interesting thing is we're given mass. If you plug in M1 times gravity to get the weight of that mass times R1, and you do the same thing on this side. So you're taking the mg and making that your force. The thing that's interesting is that the gravity's on both sides and it just cancels out. So you can really just take the first mass times radius equal to the second mass times radius. And that makes it a lot easier. Let's talk about what the radius is for our known mass, 35 grams. If this is hung at the 20 centimeter mark, then how much distance is between the 20 centimeter mark and the center? That would be 50 minus 20. So R1 is actually 30 centimeters. That's the most common mistake people make on this question, is they use the first radius as 20 centimeters. I'm going to plug in our numbers now. 35 times 30 is equal to m times 50, because the radius on this side is going to be from the 50 centimeter mark to the 100 centimeter mark. If you do all that work, you end up finding out, so 35 times 30, I'll just go ahead. I won't cut corners, I'll work it out. For those of you following along at home. So this M over here could have a mass of 21 grams. Number 7, a bike wheel has an inertia of 17 kilogram meters squared. Isn't that an ugly unit? Ugh. That's why I'm not going to have you guys calculate that on your own. It has a rotational velocity of 12 RPM. RPM stands for revolutions per minute, just like we talked about in class. If the inertia is doubled by adding a large magnet to the rim of the wheel, what will happen to the rotational velocity? So this problem, they've given us an inertia and they've given us a rotational velocity. Let's just write that down. They tell us that the inertia is doubled by adding a large magnet to the rim of the wheel. So they're giving us another inertia to work with, and they're asking us about another rotational velocity, which means the equation that we're going to use is the conservation of angular momentum. So if our I2 is double, that's just 17 times 2, which is 34. And we're looking for the second rotational velocity. So when we plug this in, it looks like this. 17 times 12 is equal to 34 times omega 2. And the unit for that will be the same as our unit was up here. Now, do you notice something interesting? We started off with a rotational velocity of 12, and then we ended up with half that. If you think conceptually about this equation and what happens, you'll remember us talking about how if you double one of these, you're going to half the other because they're inversely proportional. That's exactly what happened. So I will accept on the test that you don't even have to work this out, because a lot of people just sort of see that intuitively. That if you go from 17 to 34, if you double the I, that you're going to have half your rotational velocity in order to get them to still be equal. The next question is a little closer to that, where there's not numbers to plug in, you just have to think through it logically. If the rotational inertia of an ice skater is cut in half, what will happen to the rotational velocity? So as I was stating up there in number 7, if the inertia increases, the rotational velocity is going to decrease. If the inertia decreases, then the rotational velocity will increase. So if your inertia is cut in half, then you must have twice the rotational velocity. So that means that it doubles. Our last question has a lot of parts. This question asks you to show the proportional change in force, Fg, if the following changes take place. And then we have a bunch of changes with masses and distances. So the first thing that I want to do is tell you which equation to use. It might be obvious, but we're going to use this Fg equation. And it's got the big G, which is the constant, which I said you're not going to have to use the actual number. And then it's got 2 m's on top multiplied together and a d squared on the bottom. That's the equation that we're going to use for all of these. I'm going to slide this up enough to I'm going to jot my equation down over on the left margin. So that equation we're going to use for all of these. And what we're going to use is our rule of ones. We're going to find we're going to take anything that doesn't change and plug in a 1 for it. And then we're going to take all of our changes and plug the numbers in, like 2's or 1/2's or 3's for the different proportional changes that are going on. So if we double both masses, our G doesn't change, and we're doubling both masses. That would be 2 times 2. And then our distance on the bottom is not changing. So that's going to equal 4 over 1, which is 4 times Fg. So that will quadruple the force between the two objects if you double their masses. If we half the distance, G doesn't change. G's never going to change, by the way. The m's are not changing. And on the bottom we have 1/2 squared. So that works out to be a 1 on the top, and then 1/2 squared is 1/4. And that equals to 1 times 4 over 1. So you got to review your fraction math. If you divide by a fraction, you multiply by the inverse of that fraction. 1 times 4 over 1 is just 4 times Fg. So you can quadruple the gravitational force, whether you double the masses or whether you half the distance. What if we do both? What if we, oh wait, hold on, back that up. This is one mass is doubled and the distance is doubled. So we're going to keep our G the same.